I'm Forrest. I will be presenting this talk with my colleague Sami Sidhu, who will take over midway through the talk and present some of the slides. I'd also like to thank my colleagues at DeepScale, Albert Shaw, Daniel Hunter, and many others for their contributions to this research. And this talk is called SqueezeNAS, Fast Neural Architecture Search for some faster semantic segmentation. And what we're going to be covering today is we'll kind of start off motivating the search for efficient deep neural networks and talking about how neural architecture search can help with that problem and how it relates to automated driving. Then we'll go into some of the work out there on neural architecture search that's relevant here. Then we'll introduce our approach to applying neural architecture search to help us design efficient deep neural networks for semantic segmentation, and we call that method SqueezeNAS. We'll go through the results on that and sort of post-mortem, what was the design of the nets that the NAS came up with and how does that relate to others. And we'll wrap up from there. So before I go too deep into efficient deep neural nets and all these things, let me just kind of give a little bit of a run-up of where I'm coming from with DeepScale on solving these problems. I promise not to make this an advertisement for DeepScale, but I think a little bit of background is probably in order. So the Society of Automotive Engineers, as many of you know, have defined these levels of automated driving, ranging from fairly basic level 1, collision avoidance type of applications, all the way up to level 4 and the ability to have things like fully autonomous taxis, robot delivery vehicles, robot highway trucks, and so forth. I think a lot of you may be actually working on level 4. I think a lot of the other hot startups in Silicon Valley certainly are. But I think there's actually a ton of opportunity in the level 1 through 3 applications to make driving more convenient, to save lives, and to really add value to the human driving experience. And if any of you have experimented with something like Tesla Autopilot, which I personally feel is kind of the gold standard driver assistance system today, really fantastic things can be done in these lower levels of automation. In terms of where the kind of work that we do fits into this overall ecosystem, for everything from level 1 through level 4 or maybe even 5, you need this, maybe some superset or subset, but these are some of the core building blocks that often make sense to use. And our expertise is really in the perception space, which is why we're here with you at CVPR. And I think in terms of what kind of AI technologies we need for perception, as I'll get to, it's very clear deep learning is extremely important. For motion planning and other aspects, I think the jury's kind of still out on whether deep learning or other methods makes more sense. But in terms of perception, I would say the world leaders in everything ranging from levels 2 through 4 are making very extensive use of deep learning. So the CEO of Aurora, formerly with Waymo in his previous job, says that they've gotten huge productivity improvements by using deep learning to get the same results. And I guess implicit in this is they can get better results with the same amount of time they invest in development. Waymo, or as it previously known, Google Self-Driving Car project, has been around since before the deep learning revolution in the mid-2010s. And when they made the switch to deep learning, they got a 100x improvement in the error rate on pedestrian detection. And I imagine they further improved since then. Finally, I would also say the best level 2 highly automated driving systems make extensive use of deep learning for perception. Andrej Karpathy likes to say that a neural network is a better piece of code than anything that you or I could write or create for interpreting images and video. And as I understand it, deep learning is sort of the go-to starting point for pretty much any new computer vision problem they have to solve. So deep learning is excellent, but I would argue it's not just that we need deep learning, we actually need highly efficient deep learning. So if you look in the trunk of one of these self-driving car prototypes, I think the only exception I've seen really is Tesla's level 2 system, where they've done some really great work redesigning neural nets to fit on small platforms as well as developing their own platforms. But for all this stuff here, and pretty much the whole kind of self-driving R&D fleet, there's a trunk full of servers in these cars. If you ask the engineers at these companies what these servers are there to do, they say it's mainly for deep neural network inference. If you ask why they're doing that, they'll say we're mainly using that for perception. So vis-a-vis, perception with deep learning is the very expensive computing workload that motivates having these servers in there. But trunkloads of servers also have some major downsides. So obviously, it limits the space you can actually store things in the trunk. They're quite expensive, so you can easily spend more money on the servers than you spent on the car itself. The energy usage is significant, so we're talking often 2 to 4 kilowatts. And if you look at how much energy you burn per minute while inching through traffic in the city or in a traffic jam on the highway, you don't burn all that much energy to propel the car at low speeds per minute. So you can easily reduce your EV battery range by double-digit percentage points, in pathological cases, even up to 30, 40%. On the highway, it's a lot less than that. And there are other issues as well with kind of filling your trunk with servers. So what are the solutions to this problem? Well, if you look at what kind of hardware people are putting in the trunk, it's often very high quality hardware from companies like NVIDIA. I love NVIDIA. I actually worked there briefly. I think they have some great products, but these products aren't for everyone. So they skew towards the more expensive end of the market with high wattage, pretty expensive devices, which their main benefit is that they offer tens to hundreds of teraops per second per board that you're putting in the vehicle, with things like Drive AGX or Drive Xavier. On the right-hand side, that's the kind of stuff that we actually can use in a vehicle that you or I would be able to go to a car dealer and purchase that has highly automated driver assistance in it. These are 1 to 30 watts, tens of dollars. Getting a teraop per second would be a pretty good accomplishment there. And I think the way most of the automakers I talk to see it, they could use one of these to process data from, let's say, 1 to 3 cameras each. So if you have 9 cameras, you're talking at most 9 of these chips, and ideally more like 3 of these chips. So this is a big gap. I mean, this is an order or 2 of magnitude at least kind of gap. So how did we get to the situation where people are filling their trunks with things more like what's on the left? Well, I think it's partly an artifact of what kind of deep neural nets people have at their fingertips. So on the upper right of the triangle, you could start your deep neural net development project with off-the-shelf deep neural nets that just won kind of the top of the leaderboard, maybe the people who just won the competitions in the previous session before me at this talk. You could start with that. And it's not been optimized for computing. You could go in the upper left and look at the things where people have done some optimization for computing, but often at the expense of quality results, error rate. Or at the bottom, the kind of extreme option that you could hire a pretty big team of experienced people who can build you a new neural net design from scratch, really know how to do that, burn a lot of compute and time doing that. But I think there's another option that's only recently kind of become viable, which is neural architecture search. So neural architecture search, I would say the promise of it, at least from my perspective, is to dramatically reduce both the engineering hours and the computing hours required to develop an entirely new neural net that's optimized both for your computing requirements and your error rate or accuracy requirements. Now I'd like to hand the floor over to my colleague, Sami Sidhu, who's going to tell us more about that.
Let's talk about neural architecture search. So how do we define this? What we want is the best networks that are the best trade-off between compute and accuracy in some search space. We can define a search space by being some number of layers, channels, kernel size, connections, etc. If we put a couple of options in each one of these, the search space actually becomes quite large, and it's intractable to train every single little one, even if we have very powerful computers. So can we do better? One thing we can do is select some at random, do a random search. We can do some kind of evolutionary algorithm via a genetic search. We could do reinforcement learning or differential search. In this talk, we're going to be focusing on reinforcement learning and differential search, which our method is. So now let's go over some related work. One of the first pieces of work that really started up the field in architecture search was a paper from Google Brain called Neural Architecture Search with Reinforcement Learning from Quackly's group at Google. What this work does is use a reinforcement loop, reinforcement learning loop, where it has a controller, which is an RNN-based network, and generates a network by varying the number of filters, height, width, stride, etc. for the entire network. With these candidates, it trains it, gets the accuracy, and actually uses it as feedback to generate better and better candidates. It achieved marginally better results than what was state-of-the-art at the time on CVPR 10, and the compute it used was enormous, about 500,000 GPU hours. The search was performed on small data sets, so it's hard to extrapolate how it would work on realistic like workloads in reality. And this is a lot better than brute force, but it's still too much compute to be useful in practice. The next piece of work, also from Quackly's group, is constraining the work down to a single cell. So instead of a block level where every single layer can be different, we constrain it to a cell, a normal cell and a reduction cell, which reduces the resolution. This, you also use CVPR10 to perform a search, and then it was then adapted for ImageNet classification. This achieved fairly impressive results, doing 1.2% better accuracy on ImageNet, being 30% faster than the current state of the art. The GPU hours actually was reduced by a power order of magnitude, being 48,000 GPU hours. Some caveats are the cells are all the same, so a cell that's more optimized down the network may not be achieved because the entire network is being constrained. And this is a lot more efficient than the previous method, but still too much compute to be practical. Here's another piece of work, differential search, FVNet, which is actually a CVPR this year done by a colleague of mine, Bi-Chen Wu. And what this work does is use the gradient-based stochastic supernet that dually optimizes the convolutional weights of the network, as well as the parameters of choosing individual units. And the way it does that is using a Gumbel softmax to sample from a categorical distribution that is weighted by the learned parameters of the architecture parameters. And the results were very impressive. FVNet B achieved MobileNet v2 1.3 level accuracy, which is an over-provisioned MobileNet, while being 1.5 times lower latency. The search cost was also very small compared to the prior works, being only 216 GPU hours. And the search space is inspired by MobileNet v2, so it's very interesting to see how much lower latency was being the same search space. The way I like to think about this is that it's a very big net that contains many little experiments rather than having a controller generate little experiments to then learn from. It's really interesting to see how some researchers have been able to turn this problem inside out. Here are some other related works that we're not going to go too deep into. There's a genetic search algorithm by Google as well, AmoebaNet, and that took 75,000 GPU hours. Another work from Kwok Lee's group, MNASNet, which does latency-aware block level search, which is more related to the first piece of work we looked at, and this used 48,000 GPU hours. And finally, there's DARTS, which is a gradient-based cell search method, which is similar to the second piece of work we looked at, and this only took about 100 GPU hours. So now let's talk about applying NAS to design DNNs for semantic segmentation. So let's do a little bit of overview of the differences between classification and semantic segmentation. If you look at an image classification example, it's an image level prediction, meaning if you have a leopard in the image, you're going to predict leopard. If you move this leopard around a little bit in the image by shifting it or scaling it, the prediction should still be the same, so it's location invariant. It's fairly low resolution to determine it is a leopard, being 224 by 224, and state-of-the-art networks for image classification ranges in about 10 gigaflops. Now, if you look at semantic segmentation, like Cityscapes here, we do a pixel level prediction, meaning for every input pixel, we want to predict a classification for that. If we shift it or scale it out any bit, the output should reflect the input's pixel value. And the resolutions are fairly high. We're looking at 1K by 2K resolution. And state-of-the-art networks are about a teraflop, which is 2 orders of magnitude greater compute. And the key point that I want to emphasize is that for ImageNet classification networks, typically what you do is design networks for the task, and they're trained from scratch for the task. Whereas for semantic segmentation, you adapt networks made for image classification, and then do tweaks here and there, load those weights, and then retrain them for semantic segmentation. Here's an example of this. On the left here, you have a typical example of an image classification network. You have 4 blocks where each block does some kind of strided convolution and then following computations after that. And at the last stage of this 32 strided feature map, which is simply the ratio of the input resolution and that feature map resolution, we do some kind of global average pooling and then do some kind of class scoring. With segmentation, what we end up doing is in the 4th stage, we don't do a strided convolution and we dilate or hold the convolutions behind it so we can leverage the same weights. Then we do some kind of segmentation head. In this case, it's a 12 spatial pyramid pooling, which is very common in the DeepLab v3 architecture. And then finally, we do the class prediction and then do an upsample to bring it back to the original resolution. So as you can see, it's kind of a hacked up version of the ImageNet classification. So what do we want? We want to advance the frontier of accuracy and efficiency on semantic segmentation. Related work typically starts with an ImageNet classification network and then adapts and fine-tunes it, the DNN, for semantic segmentation. Now, our hypothesis is that if we do NAS directly on semantic segmentation, rather than starting with the ImageNet network, will this give us better results? Our method is called SqueezeNAS. It's an adaptation of FVNet, which is at CVPR this year, for semantic segmentation search. Like FVNet, we run a stochastic supernet, which means we run all units in parallel. Then what we do is perform a weighted sum from a Gumbel softmax, which essentially is weights that the network learns plus some randomness. This leads to two different types of parameters in the network: convolution parameters and then unit parameters. These parameters are resource aware, and these units ultimately end up choosing what unit gets picked in the final candidate networks. We optimize these by optimizing convolution parameters and then the unit parameters or architecture parameters of the network in an alternating fashion. And finally, one thing that we do differently is proxy training. We train directly on cityscapes and high resolution feature maps, 1K by 2K, and we train both the architecture and convolution parameters until they both converge. So we look at the training workflow. The key differences of FBNet and ours is that we train directly on the task that we care about rather than a proxy task. For FBNet, it was a 10% subset of ImageNet. We both sample the networks from the super network. We evaluate them on the validation set using the weights from the super network. We select the best DNNs and train them on ImageNet 1K. Then we do a fairly aggressive segmentation pre-training regime, doing fine-tuning on COCO and Cityscape's course, and then finally training our tasks that we care about. Cityscape's fine. Now, what did we search over? So this is our search space. We borrowed the MobileNet v2 unit, just like an FBNet, which takes in a feature map, performs a 1-by-1 pointwise convolution to do an expansion. So you might have 32 channels come in and 128 that come out of that first convolution. Then we do a fully depthwise or fully grouped convolution of some filter size. Then we finally do another 1-by-1 convolution to bring out that expanded channel size back down to the original channel size and then do a residual add. The choices for expansion, the multiplier from the input to output channels, we have choices of 6, 3, 1, and 1, and using two groups in that 1-by-1 convolution. And for the depthwise convolution in the middle, our choices are to use a 3x3, a 3x3 dilated convolution, and a 5x5 kernel. And the architecture can also pick to just skip this unit completely, where these three units would not run, and then the residual will just be the only thing running. Now, what is the meta architecture of what we're solving for? So this is a fairly common meta architecture for some semantic segmentation. This is borrowed from the DeepLab v3 Plus paper, where you have an encoder-decoder type structure. What we're optimizing for is SqueezeNAS, which is the encoder of the network. So that feeds this spatial pyramid pooling, and then that comes out, and as well as a bypass from the network, and then that's convolved and upsampled as well. And then the output is our final prediction. Let's look at some results. The red line here represents the prior state of the art when we started this work. For the same amount of compute, we're able to achieve 4 to 9% higher MIOU on semantic Cityscape's fine MIOU. Let's look at what the networks look like. On the top here, you have MobileNet classification. It's a typical ImageNet classification network where you have 4 downsample stages and units throughout the network that are the same compute. Below that, we have MobileNet v2 adapted for segmentation. And typically the way you do that is you get that last downsample stage, you remove the strata convolution, and then you dilate everything behind that. And you see that with the hold convolutions at the end of the network. So there are 3x3s that have the receptive field of a 5x5. Our work actually uses a mix of these layers, 5x5s, skinny expansion units, as well as dilated convolutions. Rather than staring at this for a while, let's do some analysis. So one thing that's interesting is that all of our searches led to heavy use of dilated units towards the end of the network without any prior. So each search is unique without having intuition from a previous search. This follows human intuition from all of the state-of-the-art papers for segmentation that lead to you have to dilate more as you go deeper into the network to get more receptive field. One thing that was also interesting was that our downsample units typically pick the most computationally expensive units when performing the downsample. This is different than typical networks where you typically just use the same 3x3 kernel you would as the rest of the network. And I think that the thing that was the most interesting is that our networks picked non-uniform compute. Typical networks, like your ResNets, MobileNets, VGG, they use the same amount of compute in every single unit. When they perform a strata convolution, they double the channels, and the compute stays the same. And in our case, we actually changed the amount of compute depending on what the network felt like it needed at that stage. And a pattern we noticed was a low compute and high compute alternating pattern, which can be explained by the network trading off spatial features versus pixelized features. If you have a high expansion, what you end up doing is performing more spatial convolutions than if you have a low expansion. Now, how long did it take to get these results? This is our table for search time. With SqueezeNAS, the SqueezeNAS results that we have, 3, 9, and 23, which are the gigamax that each of these networks are, we had a search time between 100 and 300 GPU hours. Directly searched on cityscapes using gradient-based method. If we look at some RL-based approaches, typical search times are 48,000 to 500,000 GPU hours, and they search on either proxy data sets or something small like CVPR10. Genetic-based algorithms use quite a bit of compute as well, and AmoebaNet being 75,000, and other gradient methods use much lower compute. In this case, they searched over small or proxy data sets. Here are some implementation details. We used 13 candidates per unit, which for 22 layers, which led to 10 to 24 possible networks. We randomly initialized the super networks to start, and we trained only the convolutional weights until it's stable, then switch to an alternating pattern. We train the convolutional weights in half precision and full precision for the unit parameter or architecture parameters of the network. This cut the GPU memory in half, which allows us to fit a bigger batch size, which you need for these high-resolution images. We trained a super network on C6Fine with 768 by 768 patches with flip, crop, and scale augmentations. Now, after super network has converged, we sample each candidate network via the Gumball softmax. We run each of the candidates through the validation set, and the best of these candidates, we actually run 90 epochs on ImageNet, 30 epochs on Coco, 40 on Cityscape's Course, and finally 100 on Cityscape's Fine. And then we're done. Our future work, what we want to do is do latency-aware search on publicly available hardware platforms. Since we're an automotive company, we currently target automotive-grade hardware, and we're under strict NDAs with the hardware manufacturer to release results. Since the time of this work, MobileNet v3 has released results on low compute segmentation, and our address to that is to search alternate spaces for better results at lower compute, since our results are fairly similar. And we want to release a paper publicly soon. Conclusions. What we did is created a new compute versus accuracy curve for low compute segmentation. NAS helps with this quite a bit. Some architecture patterns follow human intuition and some don't. I think we have a lot to learn from what NAS can produce. Smaller and well-designed search spaces can lead to shorter compute time. If you look at the first example we went over, the block level search from Google, anything was possible within that search space. By constraining it to a cell and constraining it to a handful of units, we can actually have tractable search times. And now, researchers can design neural architecture search spaces rather than designing individual networks.